Okay, so microphone is on. All right, so let's recap a little bit. We talked about the discriminative task, and now we are revising about naive Bayes. We said that naive Bayes is actually like a very fundamental way of exploiting this Bayesian relationship, where if we were to use naive Bayes, what we would do is that we probably would use the Bayesian relationship, and then we can keep changing this assumption of the PDF. But when it comes to LDA and QDA, we'll make further assumption about the parameters inside that PDF. A little side note, if you use LDA and QDA, actually I was going to say that, your assumption about PDF will be Gaussian. So both LDA and QDA are based on the Gaussian assumption that the distribution of x given y in a certain class is Gaussian. And as I mentioned before, actually I should have used this notation consistently, but I forgot. So actually this probability and this one is the same thing. Yeah, I just forgot to write it more concretely. So yes, in naive Bayes, the common thing that people normally do is that they will keep changing this probability and see whether or not, like, it's like you can make different choice of this probability. Pretty much the differences between them is like you will end up with different formulation. And when you have different formulation, after you derive, you probably get different boundary curves. So that's what's going to happen. And how your boundary curves would appear to you depends on the linear relationship, or maybe the relationship between the class that you have or the probability that you assume versus that input feature x in your boundary decision line. So maybe just to recap a little bit, this boundary decision is actually related to the probability of y being in a certain class given x. But then because, let's say when we write pop of y given x, which is equal to, according to Bayesian relationship, fx given y times py. But the thing is, we don't normally consider this distribution. We consider them as a fixed probability because whatever input you get, whether or not it belongs to maybe class A, class B, class C, if it's the same input, it has the same probability. So that's the reason why they would rather ignore this term. Meanwhile, this probability of being in that particular class could be different. So only the denominator, or maybe the top one here, those top terms are going to be something that you want to consider. And if you want to judge whether or not your input belongs to which class, it depends on whether or not the probability of y being in that class is higher. So if y equal to 2 is higher than y equal to 1, then that means actually input x should be in class 2 than class 1. And if p of y equal to 2 given x is higher than p equal to 1 given x, this will be the same for its logarithm value. So if you take the logarithm, just like on your right, if you take the logarithm and you get that log value of y belong to class 2 is higher than the one that y belong to class 1, then you can judge that actually it should be in this class. So that's why we call the function, or maybe the value function that we derive from this probability in logarithm space. Maybe you could consider this equation versus that equation. So you could subtract them together and you consider that log of differences. Then we can use that to make a boundary decision. So, or on the other words, that you are comparing between the log value is actually making boundary decision. Yeah. And actually, if you write differences between log of fx given 2 Okay, maybe I shouldn't use a difference. Or sometimes you can like put it together like that and see whether or not this entire term is larger than 0 or less than 0. You can use these differences to make assumption, to make the decision. So yes, you may call these differences as like a boundary decision. But the thing is, this equation is very much simplified because if you have only 2 classes, you can compare just like this. But if you have multiple classes, so that means you have to pick one and versus the rest for every computation that you have. And you see which class give you the highest score. So that could lead to like a different way of writing this boundary decision, which is, let's say, I think I'm not sure if I give the lecture about this yet. Okay. Okay, so that become an equation that maybe look like this. Okay, maybe I haven't write it here, but let's say it's the same messages as what I tried to show here. That if you put like the pop of y equal to one class versus another class, you will end up having these differences between logarithm value, right? And you can decide if these differences is larger than 0, less than 0, or equal to 0. If it's equal, that means the 2 classes have same chance given the same input. But the thing is, you can actually write this as an optimization problem where you are finding the argument max of that class where is the highest. So that means that you would run all k, it may be equal to 1 to top k, except c. So you have, if you want to compute this manually, what does it mean is that if you have k equal to maybe if just 2 classes, then you compute first time when c equal to 1 and then k equal to 2. And the second time is k equal to 1 and c equal to 2, right? Because you only have 2 alternatives. But if you have 3 classes, what would that happen? Then that means you have to compute c equal to 1, c equal to 2, c equal to 3, where k could be 1, 2, 2 and 3. This is like one and 3, and this k will be iterating from 1 to 2. So this k is that k that you are summing over. Maybe let me write it differently. Let's say this is just a set of k. Maybe it's better. And then you can say k that you're iterating or on the other words, you may say that, okay, so you're iterating over everything except that c if k is a set of 1, 2, and 3, right? So this is when you argument max, that means you have to compute every possible c in k as well. It's not just yep. So that is what it meant. And yes, you can decompose this function into some simplified form if you can make like the assumption about the probability of y given c given x, y equal to c given x. So yes, to recap, if it was naive Bayes, this could be anything, like any probability, right? But if you use LDA and QDA, then you would decompose this prob of y given equal to maybe L given x equal to, not equal to, proportional to, but we approximate it as prob of x given y equal to L times prob of y equal to L. Then you further made assumption that for LDA and QDA, this x given y equal to L is going to be Gaussian with certain parameters, and we know Gaussian will have two parameters, mu and variance. But what should we do, right? Because actually the data, like the center of this prob of x, could be different for each class, because when x is an input to classifier, that means if we can really separate this x for a certain class, the distribution of x should be different for each class. So sometimes we would use the subscript L, or in my notation, I think I use something like subscript C to denote the fact that your Gaussian is probably different. Just like in this example that I just showed previously, the star point here is your mu c, is the center of your data point. Meanwhile, the ellipsoid boundary here is your variance. So in this class, you have the same variance, but different center, because your ellipsoid is about the same size. Just like this one, you're having about the same same circle, but your center is different. So in this case, you are actually approximating that sigma c squared is equal for all classes. So that's what happened. But the thing is, when I write the Gaussian like this is actually like a one-dimensional data for two-dimensional data that is shown previously. So it should be like a vector of classes and the like covariance matrix for that data in different classes. So it would be extended into this, and maybe mu1, mu2 belong to class C, or sometimes we would just denote it as a vector of the center of that data samples distribution, the mean value. So that's what it meant. So in this case, for LDA, will be the same for every classes, but QDA will be differences. So let's first look at the LDA and see what, when we made this assumption, what does that lead to when we try to go back to the formulation of this equation. Okay, but just to recap, I think we all remember, if sigma is the same and if you compute the difference, this sigma term will actually kind of like become just a constant. And when it becomes just a constant, it will enable the fact that we can actually abbreviate this sigma to the point that it turns this differences equation into just a linear function in x. Or in the other words, if you plug in everything, like say that prob of x given y is a Gaussian, and then if we say that sigma is the same for all, this cost function will become a linear function. In X, that entire thing will be a linear function in X, which will be somewhat similar to this equation that we kind of write here, but actually, yeah. Okay. Actually, I think I should provide you some example. For LDA, okay, when we made that assumption with the Gaussian thing, maybe I'll just turn that into logarithm so it's simpler. Something like this, right? But this one is going to be the same for every term. Therefore, if we were to decompose them, that would be the same. I mean, I would just, okay. Right. But the thing is, this term, you don't need to reconsider it again and again, because for every, for an input X, that will be the same for every class YC. So this could be ignored. So maybe let me just write as But the thing is, what you want to consider here is just like the difference between the log function. So that should be something like this, right? So that will be about, here I kind of ignore pop of y equal to c for the time being. Okay, so that will be about the fact that you have to right, if we only consider two terms, but if we have more than two terms, that we have to iterate over all k in the set of classes. So that means that we can pretty much say that, okay, so that it approximately about k in small k in big class k except c, right? So that what these log terms become, because we now consider every other classes except the class C, right? But then you can also kind of like put things that are the same together, right? This and that together. So that would become is that right? Oh, sorry. Actually, we have to leave this term. We can't really put them together. Okay. So yeah, we have to leave it the same. Wait, sorry. So oh, there's no paste. Okay. Right. Maybe let me just rewrite that a little bit. That's it. Okay. I'll put it up here without replacing for a new one. Okay. So what that means is that how you make this decision boundary depends on how you would compute this and find the one with the maximum value, right? But also another thing that we can notice about is that if we know what is mu c and if we know what is mu k and the covariance, we can also compute this equation right away. I mean, if from the data point of view, like if we have the data and if we can compute this sigma that is like the boundary or maybe the standard deviation of your data sample and the center of your data sample, then we can plug it into this equation, which is like the LDA equation, and you can make the decision on your boundary. So that can happen as well without trying to solve for sigma and mu c using the linear solver, like when you solve for sigma and mu c in, let's say, if you recast this, if you put this as like you know that if we have a matrix and a vector multiply, that become like a matrix. You can think of this like a matrix beta. Sorry, not matrix. It become a vector. You can think of this like a vector of parameters beta, and you can solve for beta in the same way that you solve for the parameters in linear regression. So that's kind of like the reason why LDA and linear regression is like equivalent to one another. It's equivalent because when you learn for these model parameters, you can learn it that way as well. But alternatively, you can also try to learn from it by approximate the mean of X in each classes and the sample variance of the data in each classes. So that can happen. For the second part here from we know that when we compute the variance, we may not actually need to go as far as summation like the second round here. But I think the reason for them to have this second round computation is more like to average them. So that's what is meant for these slides. And after that, another approach is to consider the assumption of the fact that maybe previously when we say that when we use LDA, we assume that the sigma, the covariance matrix of Gaussian, is the same. But what if we enable that to be different for data in each class? So actually that means that in this equation, and this time please notice that we are using the sigma subscript c. So that means that for this class, for this case, sigma is different for every classes. Or on the other words, if you go back to this example, like in this example, what it means is that your sigma, which if you were to graphically visualize it, it's the same as your ellipsoid boundary. So you can see that for the data in red class and the data in blue class, you get different ellipsoids. So this means that actually your sigma is different for that two classes. But somehow, yes, I mean, in reality, it's different. As it's mentioned here that actually we know in prior that if our data has varying covariance, so yes, this what QDA would give you the boundary, and this ellipsoid here is like the estimated covariance that is gave to you for each class. However, if you estimate it in the same way that LDA estimate the covariance and the center, just like what you've seen previously, where you actually compute the covariance in a way that you average between them. So you get a covariance that probably look like this, where you have like a similar circle. It's a little tilt, but it's the same for two classes. But the thing is, once you plug it in and make a decision according to that decision boundary, you would get this, well, linear boundary, but not well separating the data points, because it doesn't match your assumption as much. So this is like the impact of using different tools. Different tools show to have different interpretation of how your data points are, and therefore it makes assumption accordingly. So that's what's happening. Okay, so let's continue. We are about to finish. Please don't worry, and there will be no class next time. We all be free. You should be happy to go back home and just review, recap everything. And if I miss any lecture and you want me to do it, just feel free to poke me and tell me that, okay, this lecture is missing. If I remember correctly, the classification lecture is missing. And it's missing because I remember I taught it, but it was very bad because I wasn't really prepared. Anyway, if you can understand the topic without me giving the lecture, feel free to revise it yourself, I think. All right, so let's go back to this QDA. And yes, this is going to be our discriminant function. Discriminant function is pretty much you take the logarithm over the probability of y of x. Okay, I'll put this way. I actually wrote it. Probability of y being in class C given x. Okay, it's just that. And if you take the log of that PC given x, you will get like a GC. Okay, in this slides. So yes, it will turn into quadratic boundary decision, because if we think about what we've done before with the LDA, what happened this time is that for a QDA, as we relax this assumption that the covariance is going to be different, as we relax the assumption that this covariance is going to be the same to that it will be different, what's happening is that you can't really ignore the first term. And also the last term. Oh, sorry. Actually, last term wasn't ignored. Sorry. Okay, just the first term then. So this first term will give you the quadratic relationship between your input features x. So it's quadratic in x if you look at that. And if you put them together just like what we've done before, we will probably, just like what we wrote here, so that should be equivalent to sum of k in small k in big K, except class C, negate x transpose sigma xc Actually, I shouldn't provide it here. I'll just, because it's a negate over a terms and it turns into like a positive sign. Okay, I'll put this way. But you can like simplify it further. For example, this term is sharing same x. You can put them together, but except the first one. This term doesn't share any similarity, so you have to compute them separately. This term, you sharing same x, except sigma inverse. That could be different for each and every k. And again, you have to compute this quadratic form and sort for the class that has the highest score. So you sort for that C for the highest score, and you have to compute the difference to every term that was not in that class C, like the other term. So that's what happened when you compute this. And again, you can somewhat approximate sigma C and mu C, just like what we've done previously. For mu C, you can use same technique where you compute the sample mean for x in each class. You can, of course, you can do this in your training because you know which x belong to which class already, like which data samples that belong to class A, B, C, you knew it in your training. So you can pretty much pre-compute this mu C. But what you need to do is to compute sigma C for each and every class. So you can do the same, that is you, let's say, choose only x that where the class belong, choose only input x whose class belong to that particular class that you're interested in, and then you start to compute the covariance matrix, or maybe you approximate that covariance matrix of those data samples without the need to average them. Like you don't need to average it with this term, you just pretty much cut it off. And you will have like just the covariance of your data sample in that class. After that, you can plug it in to this objective equation. Then you get the whole entire function. And then you can sort for the value in each class. But again, let's say if we say that we compute the covariance matrix, the sigma and mu here, right? When we apply this in our classification, what is the input to this decision boundary would be x, right? Because it's the x, it could be x from your validation or testing. Or on the other words, you can, how should I say? It's like this equation is like your problem setting for maybe learning for sigma and mu. If you would ignore the fact that it could be thought of as, let's say, the data from Gaussian distribution, if you ignore them and treat it like regression problem, you can compute for sigma and mu like as a whole, like a parameters, like a beta parameters, something like that. And you solve it with linear regression. That's one way. The other way is to pre-compute sigma, that is the covariance matrix, and the mu, the sample means of your data samples, and plug them into this equation. But if that was the case, you don't need to learn for model parameters anymore because you already estimate them. So all you need to do is that you just put them in this equation, and when you have an input x from your testing, you can just find that class based on this equation directly. So that's it, pretty much how you can do it. Yeah.
So when you do the training, you just extract the parameters.
Yes. Yeah, you just extract the parameters in your training sample. You don't need to do like a training when we do in the linear regression or in deep learning. You don't need to do that because now you use the property. Yep, so that's it pretty much for QDA. And this is just like a comparison between the two methods. For example, in LDA, the number of parameters depends on okay, in here is like, because all you have to do is to estimate. It's like for LDA, you can you can do the prediction of the classes based on mu. That is the mean that your data samples belong to that particular class. So that's the only parameters that you have. So if you have n input dimension and C class, so that's how many parameters did you have. So it's very small. If you think about that compared to the deep learning. But in QDA, you will have a little more because you have the covariance to keep tracking. So in some way, in my opinion, that if we can just pre-compute it like this to make a decision for QDA, I think it's still quite efficient because all you need to do is to pre-compute your covariance and your sample mean and plug that in to this equation. And this equation is just quadratic. It could be seen as very simple, yeah. But I mean, it is kind of simpler compared to those neural network method where you have like a range of parameters and all you did is asking the computer to estimate the updates for these parameters. It can take a while. Have you run the deep learning? Is it long? The lab 3? Very.
The last lab?
Yeah.
You mean for 3 layers?
Yeah.
Number 1, number 2, 3. I took like almost 2 hours to run off.
Yeah.
To draw the graph.
And that's because you can't get a closed form formulation for your parameters. 2 hours.
Yeah,
About 2 hours. But in this case, if you can estimate the covariance and the mean, it's like once you estimate these two parameters, that's it. So it's much lighter compared to those methods. But again, if your data set doesn't really satisfy this assumption, maybe the Gaussianity doesn't fit your data sample, then yeah, you can have some kind of problem with the fact that it may not well fit to your situation. Just like that we showed here that, okay, if your data sample are having different variance, right? Actually, if we think about how this data were generated, probably the variance of class blue should be something like in the vertical direction, because you can see that it's actually pretty much spreading along the vertical line, but the red one is like spreading a lot on the horizontal line. But if you made the assumption like a equal covariance for the both classes, pretty much you average the variance between them, and then you end up with something like this circle which overlapping one another. So that means it doesn't really help you as well. Yeah, but in QDA it's kind of more accurate because your estimation of these parameters are going to be fitting your situation more. That's the kind of reason why QDA performs better. Yeah. So that's it for today.